Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin lecture 17 from the course, but make sure you have watched the previous ones before viewing this one. Into the journey of the structure of atom, we have traveled about 3/4 of the distance. Yes, we have done this much course. Now when we know a lot about the structure of atom, we know about the electromagnetic radiations having a dual nature, both wave as well as particle. We also have a knowledge of the Planck's quantum theory, which is a very interesting explanation about the quantization of energy. So today in this lecture, we will begin yet another important topic into our journey towards the quantum mechanical model of the atom. This would be again a series of about 3 to 4 lectures where we be discussing all the topics which are going to lead us to the quantum model of the atom. And in this lecture, we would be discussing the shortcomings of the BOHR'S model and then the de Broglie concept of the atom. So let us begin first with the shortcomings of the BOHR'S model. So the first shortcoming of the Bohr's atomic model was that Bohr was able to explain the hydrogen atom spectrum, but when the spectrum was observed using sophisticated spectroscopic techniques, there was seen that there were finer lines also present in the spectrum. For example, there were 2-3 closely spaced lines also seen, and Bohr he could not explain these finer details of the hydrogen atom spectrum. The next shortcoming was that he failed to explain the spectra of the multi-electron atoms. He explained the spectra only of hydrogen atom, and this was valid for hydrogen-like species, the helium plus ion, lithium plus 2 ion, beryllium plus 3 ion, so on, where there was only one electron present, right? So he failed to explain the spectra of the multi-electron atoms. Then the Bohr circular orbits for the electronic revolutions, they are planar, whereas the electrons, they move in 3-dimensional space. Then he failed to explain the cause of chemical combination and the shapes of the molecules formed out of these combinations. The most important drawback came when he said that there is a definite knowledge about the position and the speed or the velocity of the electrons at any instant of time, right? So he said that he could calculate the value of the radius of the orbit, the position where the electron is present. Similarly, he calculated the speed which was fixed for that electron, right? So simultaneously he said both the speed and the position that can be told at any instant of time. But then there came a scientist, Heisenberg, who suggested that this is not possible to ascertain the position and the speed of the electron at any instant of time. There is some uncertainty always attached to it, and this is what we will be discussing in another topic that is called as the Heisenberg's uncertainty principle. But now this becomes a shortcoming of the Bohr's atomic model to assume a definite knowledge about the position and the velocity of electrons. He could not explain the relative intensities of the spectral lines. Now, if you remember, while we were discussing the hydrogen spectrum, we said that as the wavelength decreases, the intensity of the lines decreases. That means that with the increase in the value of N2, the intensity of the spectral lines was decreasing. So why is it happening so? Bohr could not explain that. So another limitation of the Bohr's atomic model. Then he failed to account for the splitting of the spectral lines under the influence of the electric and or the magnetic fields. The splitting of the spectral lines under the influence of electric field, that is called as the Stark effect, and the splitting of the spectral lines under the influence of the magnetic field, that is called as ZEEMAN effect. And please do remember both of these, what is Stark effect, what is ZEEMAN effect, because these are asked in the questions. Many a times these have been asked and the children forget that, so please do remember this. So here you can see the ZEEMAN effect. We have taken the spectrum of the sodium atom, and you can see the lines, D2 line and the D1 line. This is not D2 line, this is D1 line. And under the no magnetic field, there was a single line. We have seen these single lines in the sodium spectrum, that there were two yellow lines, right? You remember them? And now when an magnetic field is applied, what was seen was that these lines, they were splitting into finer lines. And Bohr, he could not explain the ZEEMAN effect, and similarly he could not explain the Stark effect, which was the splitting of the lines similarly in the presence of an electric field. Now let us move towards the quantum mechanical model of the atom. So Bohr's theory and its extension to the Sommerfeld theory could explain atomic spectrum, including the fine structure of hydrogen spectrum. Well, you'll say, ma'am, you just now said that the Bohr's theory could not explain the fine structure of hydrogen. Yes, I told that was correct. But then this theory was extended to the Sommerfeld atomic theory. So Sommerfeld, he tried to explain the fine structure of the hydrogen spectrum, and he said that the Bohr's circular orbits, they are not circular. Actually, the electronic orbits, they are elliptical. And with that, he was able to explain the fine structure of the hydrogen spectrum, how we will be discussing further in the course. But for now, the Bohr's theory with the extension given by Sommerfeld, that could explain the fine structure of hydrogen spectrum. But the main objections to the Bohr's theory, they were the two important developments which contributed significantly in the formulation of the quantum mechanical model. Okay, so these two developments which provided the main objections to the Bohr's theory and contributed towards the quantum mechanical model. Which are those two developments? The first is the dual behavior of matter, and the second is the Heisenberg's uncertainty principle. So in this lecture, we will be discussing only about this dual behavior of matter. So we know that matter, that has a particle nature, and the wave nature of the material objects. This was suggested by de Broglie in the year 1924, when he stated that all material particles in motion possess wave character. Okay, so what he meant by this was that subatomic particles like protons, electrons, neutrons, they also have a dual character like the radiations. Like radiations, we have already studied that they have wave nature as well as particle nature. So he said that the subatomic particles like protons, electrons, neutrons, they also have a dual character, both particle as well as wave character, and the wave associated with them, this is called as the matter wave. And the wavelength of an electron of mass m moving with velocity v, he said this can be expressed as lambda is equal to h over mv, where h is the Planck's constant, lambda is called as the de Broglie wavelength. Right? So this lambda over hv, this is called as the de Broglie equation, and the lambda is the de Broglie wavelength. So please do remember this. This is going to be very important for you to solve your numericals. So how did de Broglie derive this equation lambda is equal to h over mv? Well, the facts known to him at that time was that the radiations, they possess energy, And if E is the energy possessed by a photon of radiation, then according to Planck's quantum theory, he knew was E equal to h nu, that is hc by lambda. We also now know this, right? So de Broglie also knew this from the Planck's quantum theory. Another thing that he knew was from the Einstein's theory of relativity. What is that? He said that it is, Einstein said E is equal to mc square. That means that the energy and mass, they are interconvertible, and this equation, this is applicable for all bodies, okay, be it radiations, be it material objects, this was applicable to everything. So these two equations, de Broglie, he combined, and what we get from the combination is that hc by lambda, this is equal to mc square. Fine. So in other words, what does this mean? H by lambda is mc and lambda is equal to h over mc. Fine. So this equation, it is the velocity of light. So this is valid for only what? The radiations, because the electromagnetic radiations, they can travel at that speed. Now, what de Broglie thought was that Einstein has said that his equation is valid for all bodies. So this means that this equation should be valid for material objects also in motion. Fine. So to apply it to the whole universe, he replaced this c by v, that is the velocity of any body in motion, and hence this made a universal equation. What is it? Is that for a particle with velocity v, lambda is equal to h over mv, right? So we have replaced the velocity of light with the velocity of any object in motion. So this again is very, very important, how he got this derivation. So you should understand this. So we can say now that lambda is equal to h over p, where h is the Planck's constant and p is the momentum. This is equal to mv. Fine. Or you can say that lambda, this is directly proportional to 1 over momentum, or lambda is inversely proportional to momentum. So these are the things which you are going to be asked in the questions. So I have tried to put them in all forms possible that they are asked in the questions. So please do remember all of this. This is a very important topic for you people. Now, one of the most important achievement of the de Broglie's relationship was that he could give the derivation for the BOHR'S postulates for the quantization of angular momentum. If you remember, while we were discussing the BOHR'S postulate, we said that Bohr said what? Bohr said that the angular momentum is quantized. The value of the angular momentum mvr, this is equal to nh over 2 pi. But what Bohr did not tell us was that how he got this relationship mvr is equal to nh over 2 pi. And the credit for explaining Bohr's postulate about this angular momentum quantization goes to de Broglie. Let us see how de Broglie explained the Bohr's postulate. So Bohr said that the electrons move around the nucleus in circular orbits. And de Broglie said that the electrons, they have a wave nature. So by the virtue of their wave nature, these can be assumed to be moving in the form of wave in the circular orbit of radius r around the nucleus. Fine. And this wave, this can be continuously in phase or out of phase. So what do I mean by that? Let me explain you. So this is the Bohr's orbit in which the electrons are moving around the nucleus, and because the electrons have a wave nature, so what we say is they move like a wave. So this is the way they are moving along the circumference. Fine. So this is the wave being formed. Now what do we mean by in phase and out of phase is that if an electron, say, starts from this point, this is going to complete one wavelength. This is lambda, right? Then it is going to complete another wavelength, and so on. And this will again come up at this point. When the starting and the ending point completing one circumference, right, of the orbit, that is the same. The starting and the ending point is the same. So here one circle is finished and the other circle will again start. So this type of wave, this is called as in-phase wave. So this will keep on continuing, and we say that the electrons, they do not lose energy, gain energy while moving in an orbit. So this wave is going to continue till the electron is moving like this. Then another possibility is that the wave, if it is starting at one point and it ends at another point, what is going to happen is that there is going to be a destructive interference, right? So this wave, this is out of phase, and ultimately because of the destructive interference, this wave is going to die out. And such waves are not going to happen which are going to die out. So only those orbits are possible where the waves are in phase. When they are out of phase, that is not possible. Fine. Now I hope you understand. Now if this is the lambda, right, of one wavelength, 1, then it is going to be 2, 3, 4 and so on. So how many wavelengths are going to complete over here? That is going to be n lambda. Okay, I hope this is understood. Then let me move to the next slide. So the circumference of the circular orbit, this must be the integral multiple of the wavelength of the wave associated with the electrons. Now it is clear to you that the circumference, that is 2 pi r, right, and it should be an integral multiple of the wavelength, n into lambda. And if it is not an integral multiple, then the wave would interfere destructively to cancel each other, thus destroying itself, right? I hope this is clear, because it is very important to understand all the concepts very well. So we have 2 pi r is equal to n lambda, or lambda is equal to 2 pi r over n, where r is the radius of the circular orbit and lambda, this is the wavelength of the electron wave. And according to the de Broglie relationship, lambda is equal to h over mv, right? So combining these two equations 1 and 2, what we get is 2 pi r over n is equal to h over mv. Fine. So 2 pi r over n from here and h over mv from here. Both are lambda. So we get 2 pi r is equal to nh over mv, or we get mvr is equal to nh over 2 pi. And this was what the BOHR'S postulate was. Fine. I hope it is clear how we have derived the Bohr postulate about the angular momentum from the de Broglie relationship. Okay, now another thing which I want you to visualize over here is that what is n in this case? N over here, we are saying this is the multiple of the wavelength, right? And in this case, what is n? N is the number of orbit. Fine. So both the cases n is the same. So this means that n number of waves will be present in the nth orbit. In the first orbit, there will be one wave. In the second orbit, there will be two waves. In the third orbit, there will be three waves. Fine. I hope this is clear, because this is asked in the questions. So you should know about this. How many number of wavelengths are in third orbit? If that is the question, the answer is so simple. Fine. If you have a knowledge, you are going to do very well. So the angular momentum, now this is the integral multiple of h over 2 pi. And the units of angular momentum, they are the same as the Planck's constant, that is kg meter square second inverse. The most important thing from here that you have to remember is that n, this is equal to the number of wavelengths in an orbit, and this is equal to the orbit number. So please do remember this. This is very important. Now we've been talking about the wave character of electrons. Similarly, it is going to be for protons, neutrons. So what we are talking is about the wave character as well as the particle character of the microscopic objects. What about the macroscopic objects? We, the car, the scooter, do these also exhibit wave character? Well, every object in motion has a wave character. So de Broglie said that, and we agree with him. But the wavelengths associated with the electrons and other subatomic particles which have a very small mass, they can be detected experimentally. But the wavelengths associated with the large objects, they are so short because of the large masses that the wave properties cannot be detected. We do not feel that a car is moving like a wave. We feel that it is moving in a straight line. We cannot see the wave nature of the car moving, right? Why is it so? Because the car has such a great mass. Let us see it in terms of numbers also. So the de Broglie equation, when it is applied to macroscopic object, an object of mass say just 0.5 kg, car is having such a big mass. I'm just talking about a 0.5 kg, say a cricket ball, and this is moving with a velocity of 20 meters per second. Okay, so we have lambda is equal to h over mv. Putting the values, what you will get the lambda to be is 0.6626 into 10 power minus 34 meter. So this is such a small value, such a small value. Okay. And if you see this similarly for a microscopic object, an electron with a mass 9.1 into 10 power minus 31 kg. This has a velocity in the order of 10 power 6 meter per second. And the lambda, if you will calculate, this is going to come up to 7.2 into 10 power minus 10 meter. That means 7.2 Armstrong. And this is what we can detect experimentally. So I hope you can understand that the wave character is present in the macroscopic objects, but it is not detected because of the wave length being so small. Fine. So the de Broglie equation, this would be applicable only to the microscopic objects. Fine. I hope all these things that we have covered so far, they are very clear to you. Now this would be all for this lecture. We would be continuing the lecture in the next one also, wherein we will be discussing a few more points related to the de Broglie concept, and then we will be doing numericals based on this concept. I hope you had a nice time. So please do click on the like link and also do subscribe to our channel H2O. Click on the bell icon to get a notification as and when we put up a new lecture for you. So please do click on the like link. I hope you are really enjoying with me. And if you have any doubts still, please do mail us at h2ochemistry@gmail.com. We'll be really glad to help you all. So meet you again for the next lecture. Have a nice time. Enjoy yourself. Enjoy your studies. Till then, bye-bye.